You guys are gonna have the exam before us. Yeah. So you better tell what's on.
Hey, so first of all,
Is involving
Contact resistance.
will that resistance just be given? Like it's not a company.
no, it's a case by case thing. So
I might
almost
try
always-
to.
And then the second thing is I figured out I got your email about this. For some reason,
A lab,
I have like 7 outside of this, and yours is only that first.
and then
Oh,
the next term on Monday.
Yours like 34.47 plus 193. And I thought like it distributed it to.
Of course,
Probably it's, I think I might have missed that.
I think it's just two
Let me
for
double
us.
check that one.
Okay.
407.
At least our lab doesn't. Because I don't think
Do we?
we had a 6A, we had exams. Yeah, it's so bad, but.
I thought we had exams for the.
You're 16. You said he's. So everything is like so bad.
Really? Which ones are some of these exams?
Yeah, it's just these next 2 weeks are just. That's just the grade. Oh yeah, 10%.
So the report, it's just the questions and the worksheets, the MATLAB.
The lab report is just that.
I think so.
Because we didn't really make much.
Yeah, so the data reduction is the question. I reported the permanent review is just.
The thing that you read the module, the reading the module. If there's a map, read the module. We don't make a lab. We don't actually make a lab. All we do is just like answer the question.
Just straight up
files. We make a lab. It's not gonna have like a report, right? It's just like coding and then answering the data question.
Oh, we didn't go. Oh yeah, you already had it.
Yeah,
He doesn't go like anything about how to type up the.
No, he didn't.
Okay, so yeah, it's just a question.
He said the we asked him about it. It's just like he has to answer his question.
Try to go in detail.
He said, he just said,
It made sense, but I'm like, oh.
when you answer this answer, what's that? What's the other way? Some of the questions they answer like one or two sentences. Like one of the questions they answer like one sentence. Yeah, that's what I did. Yeah. So like, he said all the questions should be like one paragraph. Yeah. And the one that how long should it be? It should be like half a page overall. Like the 6 questions, it should be half a page. It should be more than a page.
No. So it's everything before and last one.
Anything off of Friday.
Yeah. I'm going to rush.
Oh yeah, I think COVID. So instead like one year I kind of want to get that over with.
Is there?
Yeah, I want to get that over with. You had a pay right down.
I'm telling you though, while you're sitting here.
It was like
The whole video, he's like an episode, right? That was, I guess I need that one. What?
when he said our exam is only on chapter 2.
Wait, the whole was on chapter 2.
But our exam.
Oh, I don't know. Oh, really? I have no clue.
Yeah, he said it's just all chapter
Did you get it?
I did.
I think I made it pretty good. Other question, sir?
Why would you change the left?
What was that from?
You might give us different questions.
We're just here all day, basically.
Yeah, 431.
Yeah.
Oh, no, not here.
Well, yeah.
Wait, you guys have 401?
Yeah, probably tonight, right?
Well, on Monday, I was dead. Like,
COVID told me, COVID said like you're like, you didn't want to do anything.
no, it was like,
We're here all day.
We're here all day.
I'm here all day.
I'm here all day.
right? And it's like, and then it hit 9 p.m. It was still left, and I was like, no, I'm not going to take
I'm playing with you.
That's why, bro. I'm like, this is the day. I'm like, oh, dude, I'm so tired.
I just stopped taking notes at 9.
He goes fast, right? In person stuff?
He took till, class was at 9:45, right? He took till 9:35. He didn't let us go on like chapter 2. It's like, that's
That's like a whole, bro. Did you do homework after that?
what?
Did you do homework after that?
That was
Yeah, I'm gonna be tired tonight, dude. Because today my busiest day. I spoke.
I had lectures from 1 till 2, so I'm like, so I'm just gonna go home. Yeah, we should meet up once, right?
Yeah.
Do a lot.
Do a lot. That's a COVID thing.
In the lab, study for
407.
407.
Oh, yeah.
Yeah.
Let's do it that Friday.
Yeah, do that. We can work on this together. Hey, want to go like early morning? Like,
Yeah.
today?
Yeah.
Because I'm working. I'm so tired.
Well, so you work until like,
Oh, yeah.
what's that, like 10 or?
So we start closing, right? But the closing process takes like about 2 hours. So I get on like a 10 a.m. I'm tired. I'm tired already.
All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everybody. How's everyone doing today?
Pretty good.
Good, good. Everyone's feeling good. Seems lively in here, which is good. Okay, so today we're starting something new. Okay, guys, maybe we're gonna get started today, guys. Okay. So today we're starting something new, and so the lecture today is going to be on. This is going to be the start of our unit on convection. So the lecture today is not going to be on the midterm, and so you don't have to worry about that. But this is going to set us up for the second midterm. Okay. Let me go ahead and write that down. Okay. And so you don't have to worry about it, but don't forget it. And so I think that tends to happen for the lecture right before the midterms, that things kind of get lost. So don't forget this lecture, but you don't have to worry about it for Monday. Okay. So just another reminder that Monday is our midterm exam. So make sure everyone is here. And so everyone that's here is great. And so just do this again on Monday, and you'll be able to take the exam. So that'll be a good thing. Okay. So everyone on Zoom, just make sure you plan to be on campus on Monday, because there's no plans to give the exam virtually. Okay. And we've talked about the exam already. So we've talked about what the format of the exam is, what you can bring, and everything. So just kind of refer back to those those past lectures. But just really quickly, just in terms of what you can bring a sheet of notes, 1 8.5 by 11 sheet. You can bring a calculator. You're going to need the calculator, so I'm working on your exam right now, and there is some computation. So make sure you bring a calculator so you can solve those. Bring a writing utensil, of course, and that's it. And that's the only things you can bring to the exam. Okay. All right. And so, are there any questions I can answer before we get started today? Okay. All right. So let's go ahead and get started. Okay. So remember, today's lecture not on the midterm, but still important to know. Right, and so this is going to be the start of our unit on convection. So this lecture notes in particular, it's called Introduction to Convection. All right, and so that might seem kind of like a strange title, because we've been working with convection up to this point, right? Right, and so it's not like it's something new to us, and so we've seen it before, right? And the way that we've seen it is in terms of Newton's law of cooling, right? And so we said that the heat transfer that's due to convection is equal to H times A times the temperature difference between the object or the surface and the fluid. Okay. Right. So this formula here was Newton's law of cooling. Okay. T infinity here is the ambient temperature. Or in other words, you can say it's the fluid temperature. Okay. And T here is the surface temperature. Okay. A here is the surface area of the object. Okay. And H here is our convection coefficient. Okay. right? So pretty straightforward. You know, we've been working with this, and so you know, you would think that's that's really all there is to convection. In a lot of ways, it kind of is. And so you know, if you have all the quantities here in this formula, then you can compute convection heat transfer, and that's really all there is to it. Okay. The problem then is kind of getting to that step where you know all the quantities here. Okay. In particular, we haven't really talked about this guy much at all. Okay. So in all the problems that I've given to you, or all the problems that we've seen so far in the class, the convection coefficient has either been given to you, or we solve for it through some indirect way. Okay. But for all intents and purposes, we can say that this has been given to us, so far. And I think the way I think most of us understand this convection coefficient is very similar to how we understand the thermal conductivity, right? And so when we talk about conduction through a solid, one of the things that we always have to keep in mind is what is the thermal conductivity of that material, right? And what we said before was the thermal conductivity K, that expressed how easily heat can move through that solid, okay? And so in the same way, this H, represents how easily heat can transfer to the moving fluid. I know the units for H are slightly different, and so I think the units for H are watts per meter squared Kelvin, whereas the units for thermal conductivity is watts per meter Kelvin. But essentially, they have kind of the same physical interpretation. Okay? And so what's the issue? And so, why am I making such a big deal of H? Okay. The reason I'm making such a big deal of H is that unlike the thermal conductivity, this is not a property of the material. And that might seem like kind of a minor thing, but it's actually pretty major, right? Because when you think of material properties or properties of the material, you think of things like density, you think of things like the thermal conductivity, you think of things like the Young's modulus, right? So all of these things, what they have in common is that you can look them up in some kind of data table, right? So you go to like a material data sheet, you look up what the density of water is, right? You look up and see what the thermal conductivity of aluminum is, right? H you can't really look up, and and there's a very good reason why you can't do that. Okay? Because not only does H depend on what type of fluid that we're using, it also depends on the fluid mechanics of the flow. Okay? Okay. And so what do I mean by fluid mechanics? And so it depends on things like the velocity of the fluid. Okay. Depends on the direction of the flow. And it also depends on, a lot of what I like to call the nature of the flows, whether the flow is turbulent versus laminar, or things like that. Okay. Okay. The thing that all of these have in common is that, these depend very strongly on the situation that you're looking at. Okay. Oops. you can't just look these up in a table because, it's going to be different. Right? So if you have flow of air, through a classroom like this, that's going to be different than the flow of air over an airplane wing, which is going to be different than the flow of air that goes through your computer that's going to cool your computer parts, right? And so the fluid mechanics, because they change in every situation, it's going to make the value of H change every single time too, which makes H normally very, very difficult to estimate. Okay. Okay. And I'll add a qualifier to that. It's very different. It's very difficult to measure H quickly. Okay? There's ways that you can compute H, and in fact, we're going to spend the next few weeks talking about that. And of course, you can run a lot of simulations to compute H as well. But you can't. It's really hard to just kind of look at a situation and say, the convection coefficient for this is this, right? So even in this room, right? Even in this room where we have kind of a light airflow that's going around. I can't even tell you, what in the right ballpark of what H would be, okay? Because it depends so strongly on the fluid mechanics. But if you ask me, what's the density of water, I can tell you just right off the top of my head. So the density of water is, almost 999 kilograms per meter cubed, right? Because that's what you can look at the table. Because water is going to be water. The material properties of water are going to be the same no matter what situation you're in. I mean, of course, I know it depends on temperature a little bit, but it mostly is the same. But because H has such a strong dependence on the fluid mechanics, you have to kind of measure it and take it, on a situation by situation basis. And that's what makes it really difficult to estimate. Okay? And so because of this, throughout this whole unit, we're going to be focusing on just convection. We're going to draw on a lot of your knowledge of fluid mechanics. And so, the prereq for this class is fluid mechanics, EGME 333, right? And so hopefully you've taken it. I mean, you should have taken it if you're in this class. But hopefully you kind of remember some of it because we're going to be pulling a lot of knowledge from that class. Okay. All right, and so that's kind of just the kind of the introduction of kind of where we're going to go over the next few weeks, and kind of motivating what we're going to do. Okay. All right. Any questions on any of this so far? Okay. All right. So let's start talking about a very important concept from fluid mechanics, and you may or may not have covered this. I think it's kind of a niche topic that comes at the end of fluids. But I'll kind of explain it from scratch, and that's this idea of the boundary layer. So how many of you in your fluids classes you guys went over the boundary layer? So about some of you guys. So that's about what I expected. So I know some faculty or some instructors cover it, some don't. And that's okay. In reality, it's the boundary layer is. It is a pretty tough concept. And so I can understand why some instructors kind of leave it out of the introductory class and you learn more about it in an advanced fluids class. But for what we're going to do, the boundary layer is really important. Okay. And so I'll give you kind of the basics of the boundary layer. Okay. And so the basics of the boundary layer is that whenever you have fluid flow that flows past a stationary object, okay, what tends to happen is that you have this thin film of fluid that forms on the kind of right on the outside of the surface of the object. Okay. right? And so the canonical picture looks something like this. So we have fluid that's flowing like this, okay? And here is our object, okay? And so for now, we're going to assume our object is just a flat plate. And so we have fluid flowing against the flat plate, okay? And then what you have is something that looks like this. And so you have a layer of fluid that kind of builds on the surface. And we call this the boundary layer. Okay? Where one quantity that we're interested in is the thickness of the boundary layer, which we usually give the symbol delta. Okay, so this delta here is the thickness of boundary layer. Okay. Okay. And so let me label a few more quantities here. And so let me say that the fluid that's flowing past the object, it has a velocity u infinity. Okay, so this u infinity is the velocity of what I like to call the free stream. Okay. And this is more or less, we can assume that it's constant. Okay. And then the surface here, we're going to assume that the surface is stationary. Okay. All right, and so, just to kind of summarize, we have a free stream condition. And so we have, fluid flow. This could be any fluid. And so I think most people think of air when they look at an image like this, but it really could be anything. It could be water, it could be oil, it could be honey, it could be sriracha, whatever fluid is your favorite. Okay. And we have a solid object that's kind of impeding the flow. So it's kind of standing in the way. Okay. Okay. And so let's describe what this boundary layer is. Okay. And so if you look up kind of the definition of boundary layer on Wikipedia or in your textbooks or anything, I always find that it's a very kind of convoluted definition of it. Okay. And I think it kind of fails to capture, what the boundary layer is really truly about. Okay. And so the definition that I like to give for boundary layers is the fact that it's basically a transition zone. You can think of it like that. Okay. And what's transitioning is, or what's being transitioned is the conditions at the solid surface and the conditions at the free stream. Okay. Okay. Say it again. VW. Oh, okay. Right. Okay. Transition zone. So what do I mean by that? And so, in the free stream, we have a certain velocity, right? And so in the free stream, our velocity is u infinity. Okay. Whereas at the surface, our surface is stationary, right? And the thing with fluids is that whenever you have fluids that flow past a surface, the fluid has to match the motion of the surface that it's connected to, right? So that's what's called our no-slip boundary condition. So if you remember from fluid mechanics, that's a condition that we usually apply, when we solve Navier-Stokes. Okay. And so in this case, since our surface is stationary, that means the velocity is 0. Okay. And so you have two kind of big extremes here where we have, outside the boundary layer and in the free stream, we have a velocity of u infinity. Whereas at the surface, we have a velocity of 0. Okay. When you have two distinct values like this, right, where the fluid has to go from 0 velocity at the surface to some velocity at the outside, the transition between these two has to be smooth. Okay? Okay. Right, and so you can't just go from one point on the surface, right? And so on the surface, you know, you might be chilling, you might be at 0 velocity, you're just kind of sitting there relaxing. You can't just go straight from that and you just take one step outside the surface and all of a sudden you're moving at U infinity, right? That can't happen. And so what needs to happen is that there needs to be a zone where the velocity slowly and smoothly transitions from the surface condition to the free stream. Okay. And so if I were to draw, if I were to draw the velocity distribution inside the boundary layer, you know, it might look something like this. Okay. And so what I've drawn there is a distribution of the velocity where, you know, near the surface, you can see here that we have no velocity. Okay. But at the edge of the boundary layer, you can see that the velocity reaches U infinity. Okay. But it doesn't do it, but it doesn't do so very abruptly. And so it does so, you know, through this kind of smooth function right here. Okay. Okay, and so, you know, the purpose of the boundary layer is to make sure that this transition is occurring smoothly. Okay, because without the boundary layer, you would have kind of a very abrupt transition from no velocity to the free stream velocity, and a lot of times that's just not a physical thing to do. Okay, you know, imagine what would happen if you put like a piece of paper out there, right? And so you put a piece of paper, you know, in a situation where you have 0 velocity here, and all of a sudden U infinity here, right? That paper would just get wrecked, right? Because, you know, you have you have one part of the paper that's stationary and the rest just wants to get pulled, you know, with U infinity. And so that smooth transition is really important for, you know, to kind of maintain, you know, it's important for maintaining conservation of mass, conservation of momentum, and a lot of different things. But, you know, we're not going to get too much into the fluid mechanics because, you know, this is a heat transfer class. So all I want you guys to remember is that the boundary layer is for transitioning, okay? Transitioning between the surface condition and the free stream condition. All right. Any questions on this? Okay. All right. Let's talk about the thickness of the boundary layer. And so the thickness of the boundary layer, you know, even though I've drawn it as kind of a distinct line right there, it doesn't have an exact definition. Okay, the boundary layer is not really a distinct thing, and so it's if you try to look for it. So if you look at kind of airflow over an airplane, or even if you like run water in your sink, right, and you look at the surface of your sink, it's a little bit hard to visualize because it's not a distinct cutoff, right? And so it's not like the fluid turns a different color, you know, once it's inside or outside the boundary layer. So, you know, the cutoff for the boundary layer is a little bit vague, okay? But we can come up with kind of an approximate definition of this thickness, okay? And so the approximate definition that I have for the thickness of the boundary layer is the distance you have to travel away from the surface to experience the free stream conditions. Okay. And I'll put free stream conditions in quotation right there because what people define as free stream conditions differs depending on, depending on your application. But for our applications, what we can say is that if you measure the velocity at the tip of the boundary layer, okay, what we can say is that we've reached the end of the boundary layer once the velocity reaches about 99% of the free stream velocity. Okay. And so if we were to go into the mathematics of the boundary layer, what you'll see is that the mathematics are very similar to our case with the fins, right? And so there's some decaying exponentials in there. And so it's very hard, just based on the mathematics to say that, the velocity is 100% of the free stream one. And so just to kind of make it reasonable, we say that once the velocity gets about 99%, then we're outside the boundary layer, and that's the thickness. Okay. All right. And I want to give you kind of a practical kind of note here too. And so, we're talking about this boundary layer, about how it's important. And from the image here, it might look like it's ginormous. But in most situations, the boundary layer is actually going to be incredibly small, which makes it even harder for you to look at with your naked eye. Okay. Okay. The only cases where you can kind of very visually see the boundary layer occurring is for when you have a very, very viscous fluid. Okay. And something like honey, something like molasses, right? So that's going to give you a boundary layer that you can actually visually see. Okay. Okay. Any questions on this? Okay. All right. And so let's talk about viscosity, because that's another important quantity as well. Speaking of viscosity. So viscosity plays a very important role in in boundary layers. And so viscosity, hopefully something you've talked about a lot in your fluid mechanics class. But kind of in a nutshell, viscosity kind of measures how well momentum can travel into a fluid. Okay. And that phrase might not mean anything. And I tried in my head to make it sound like it makes more sense, but it came out just how I thought about it. So let me give you an example. And so, if you have a solid object, and so let's say you have a block of wood, right? So let's say you have a block of wood, it's fairly tall, okay? And so let's say that you attach the bottom of the block of wood to a roller, right? And so let's say you put it on like a rolling cart. And so what happens when you push just the bottom of a cart? Okay. For a block of wood, the entire thing is going to move, right? Because the wood is a solid piece of wood. And so you push the bottom, the whole thing moves because it's a solid object. If you think of kind of the analogous situation for a fluid, right? And so let's say you have a tub of fluid, and on the bottom of the fluid, you have a conveyor belt, right? And so let's say that you start moving the conveyor belt, so the bottom of the fluid is moving along with the conveyor belt. Okay. What do you expect to happen at the top of the fluid? Right, and so it might move, but it's probably not going to move as quickly as the bottom because it's a liquid, it's a fluid, right? And so those are kind of your two extremes. And so on one extreme, you have solids where, what I like to think about when I think of solids is that motion or momentum information travels instantaneously through the solid. Okay. And so to kind of put it in more plain words, so if one part of the solid moves, then everyone's moving because it's a solid object, right? Okay. Versus a fluid, right? So the thing that's different about fluids, or one thing that's different about fluids versus solids, is that it takes time for momentum information to travel through the fluid. Okay. Okay. And so if you move one part of the fluid, okay, maybe eventually the rest of the fluid will catch on and they'll move as well, but it takes time. Okay. Okay. Right. And so the amount of time that it takes for a fluid to react, or for the amount of time for momentum to travel through a fluid, that's modulated by the viscosity. And so if you have a fluid with a higher viscosity, one way that you can think about it, fluids with a higher viscosity kind of act more like solids versus liquids. Okay. Okay. And so kind of correlate this with how you understand what a highly viscous fluid looks like, right? And so I think probably the one fluid that has high viscosity that everyone thinks about is honey, right? And so for honey, if you, let's say you have a big tub of honey, and let's say that you are really upset at it for some reason, and you punch the tub of honey, right? That's going to feel really different than punching a tub of air, right? And so if you punch a tub of air, you don't feel anything because there's hardly any viscosity in air. But if you punch a tub of honey, right? I mean, your hand should still go through, but you're going to feel a lot more resistance because the honey acts a lot closer than a solid, right? And if you take your same fist and you punch a solid desk, that's going to feel different as well. And so think of honey as kind of existing somewhere in between a solid desk and air. Okay. All right, and so the formula that kind of expresses this fact, the formula that expresses this, this behavior of momentum is the shear stress formula. Okay. Okay, and so what we have is shear stress is equal to the viscosity multiplied by the derivative of velocity. Okay. Where this mu here is viscosity, u, and this quantity right here is derivative of viscosity. Okay. And this tau s right here is the shear stress. Okay. And you can think of the shear stress as kind of the rate at which momentum is moving throughout your fluid. Okay, so the higher viscosity that you have, the more shear stress you're going to have, the faster momentum is going to travel. Okay. Okay. And so that was a review of fluids, although probably that was presented in a different way than probably what you learned in fluids. I know that's kind of different from how I usually teach boundary layers, but But I think it serves us well here because now we're going to connect all this fluid mechanics stuff to thermal. Okay. All right, any questions on any of this? Okay, all right, so that's the fluid mechanics of the situation, right? And so, just to kind of sum it up, in fluid mechanics, we have a boundary layer, okay? Where the boundary layer is this transition zone between the surface conditions and the free stream. And we have this idea of the viscosity, which acts as kind of the modulating factor for how quickly momentum can travel, okay? I want you to kind of remember those concepts as we talk about the thermal side of it, okay? All right, so let's talk about thermal boundary layers. Okay. And so thermal boundary layers, they exist, or their existence is, necessitated in a lot of the same ways that the velocity layers. Okay, and so thermal boundary layers. Oh, thank you. Yes, that is. It's supposed to be derivative of velocity. Thanks for catching that. Yes, that would be weird. The derivative of viscosity. That doesn't make any sense. Okay. Okay. And so just like in the fluid mechanics case, the thermal boundary layers are going to be a transition zone between the thermal conditions at the surface and the thermal conditions of the free stream. Okay, so let me go ahead and draw the same figure that we did before. Okay. So let me draw our boundary layer here. Okay. But instead of a U infinity, now instead we have a T infinity. Okay, so this T infinity is the free stream temperature. Or what we've been calling it up to this point is like the ambient temperature. Okay? Okay. Right, and so we have our ambient temperature. We also have our temperature of the surface. Okay, so this is TS. And so TS is the surface temperature. And so usually in convection situations, we have an object that's hotter than the fluid, although that doesn't necessarily have to be the case all the time. And so I'm going to draw this profile here, assuming that TS is higher than T infinity. Okay. Right, and so let's say that T infinity is less than TS, and so this boundary layer is going to provide a zone where you can have this kind of smooth transition from the surface to the free stream. Okay, and that's what the thermal boundary layer is. Okay? And just like in the fluids case, we have the thickness of the boundary layer, okay, which we'll call delta T. Okay. Which is different, okay? And so a lot of times your thermal boundary layer is going to have a thickness that's different than your velocity boundary layer. And so that's why I give it a different name there. Okay. Okay. And so just like in the fluids case, okay, this transition is smooth. Okay. And so you don't have any abrupt changes in temperature. Okay. And just like in the fluids case, we have a key property in our fluid here that's going to aid with in this case, the energy transfer. Okay. Okay. And so when we were talking about fluid mechanics, we're often talking about momentum. Okay. And so when we talk about momentum transfer in a fluid, we were talking about the viscosity. But for energy transfer, we have a different property that we're going to be concerned with, and that is the thermal conductivity. Okay. All right. And so the formula that we have that kind of illustrates this energy transfer is Fourier's law. Okay. And so I'm going to give the flux version here. Okay. And so what we have is Q flux is equal to minus K. I'll do KF, so K for the fluid, okay, times partial T, partial Y. Right, so here is our heat flux. Okay. KF here is our thermal conductivity. Okay. And this partial T, partial Y, this is our temperature derivative. Okay. All right, and so Fourier's law is something that we've seen before, right? But hopefully now that you've seen it alongside the fluid mechanics, you start to see the parallels, right? And so let's compare this to our shear stress formula that we had above. Okay. And so for shear stress, just remember we had our viscosity multiplied by our viscosity multiplied by our velocity derivative. Okay. Whereas with Fourier's law, we have the minus sign. Just for consistency, I'm going to change the derivative to a normal one, but but it doesn't make that big a difference. Okay. All right, so hopefully you can see that these two formulas, that we kind of talked about in very different contexts, look very, very similar, right? And that's not a coincidence, right? And so that's why, kind of in kind of the broader engineering world, thermal sciences and fluid sciences, they're often kind of coupled together. And so if you're an expert in fluids, that means you already kind of have a lot of expertise in thermal as well, just because their formulas are very similar and the concepts are all very similar. And this is just one really great example of that. Okay, and so we have two formulas here. They both kind of express transfer of some kind, right? So on the left here we have a formula that expresses momentum transfer, whereas on the right here for Fourier's law we have a formula that expresses energy transfer, or heat transfer, but they're structured very, very similar. Okay, and what I want you to highlight from this is that the viscosity and the thermal conductivity, they play key roles in determining how easily stuff gets transported in the fluid. Okay. right? And so we have strong parallels here between fluid mechanics and heat transfer. And so that's going to be a theme for this entire unit as well. Okay. And so until we get radiation, you're going to get a steady dose of fluid mechanics. And so, I'll try my best to kind of review stuff as we go along. And so I'm not just going to drop you into the fluids. I'm not going to ask you to solve Navier-Stokes just right off the bat or anything. But hopefully, a lot of the concepts and a lot of the intuition that you gain from fluid mechanics, is going to serve you well here because there's a lot of really strong parallels. Okay. All right. Any questions on anything that we've talked about so far? Okay. All right. And so let's kind of bring this back. And so we spent all of our time talking about fluid mechanics and all this stuff and boundary layers, and all that's great, okay, and all that's really cool. But our end goal here, what our end goal is that we want to use this knowledge to compute H, okay? Because that's what we really want, right? And so, the question is, how do we relate all of these things to H? Okay. Well, let's use this Fourier's law. Formula here and relate it to Newton's law of cooling. Okay. Right, because from Newton's law of cooling, what we know is that Q convection is equal to H. And I'm using the heat flux version, and so I'm not going to multiply by area. Okay, let me add an S right there. And so from Newton's law of cooling, we know that the heat flux that comes from the surface due to convection is equal to H, our convection coefficient, multiplied by Ts minus T infinity. Okay. But what we've also seen is that based on our equation up here, this is also equal to minus Kf times dt dy, okay? And since dt dy is going to change in the boundary layer, we need to be specific here, and we say that we're going to evaluate the temperature derivative at the surface. Okay? Right, and so we can kind of rearrange this this expression here to get a formula for H. Okay, and so if we divide both sides by Ts minus T infinity, right, what we get is H is equal to minus Kf dt dy evaluated at y is equal to 0, okay, is equal divided by T minus T infinity. And so we arrive at this formula for H, right? And so it doesn't seem that bad, right? And so we have the temperature difference on the bottom. And so that's something that we've been working with this whole time. So we can take the difference in temperature. Oh, excuse me, this should be Ts. Okay. And so we can take the difference in temperature between the surface and the fluid. That's easy enough. We've done that a bajillion times now. Okay. Next, we have the thermal conductivity of the fluid. But again, that's just a material property. And so, you can look that up in a table. That's fine. Okay. The thing that's going to be difficult to measure here or to compute is this guy. Okay. And the value of this derivative here depends strongly on the nature of the boundary layer. Okay. And so let me first say computing this very hard. Depends on boundary layer and fluid mechanics. Okay. And for those of you that did cover boundary layers in your fluids class, probably the prevailing feeling that you probably had coming out of that unit was that boundary layers are really fucking hard to analyze. And so probably you spent, for those of you that did cover it, you probably learned a solution of the boundary layer equations called the Blasius solution. And so even the Blasius solution, which is the simplest, literally the simplest boundary layer that you can do with a ton of assumptions that are not valid in a lot of cases, by the way, that probably took you 2 whole lectures to go over the Blasius solution, and that's not par for the course. That's not uncommon. Okay, and so boundary layers, even though I think we have a good kind of general understanding of what they are, analyzing them to any kind of numerical or quantitative capacity is really, really difficult. And so, if you have a quantity here that depends strongly on something of the boundary layer, you're kind of going down a rabbit hole, and it's not a rabbit hole that you want to go down, because it's one that will take forever and forever. Okay, and so even though we have a formula for H right here, and it seems like we're so close to having a good formula for H, this really is just not that useful for us because it depends so strongly on that derivative. Okay? Okay. All right. And so even though we can't use this formula to compute H, we did come away from this journey with a couple key facts. Okay. Right. So it wasn't all for naught. Okay. Okay. And what we learned from this is that we learned what kind of the rough factors that contribute to the value of H. Right. And so the first factor that we learned was that the value of H here depends on the thermal conductivity of the fluid. Okay. And so if your fluid is made of a material that's naturally good at conducting heat, that means your convection coefficient is going to be much higher as well. Okay. And so if you have something like liquid mercury or some kind of liquid metal, that's going to conduct heat way better than air. Okay. Because metals by design are already very conducting. And so that's going to produce, much higher convection coefficient. Okay. And the other thing that we learned is that the value of H depends on the temperature gradient at the wall, or in other words, it depends on the boundary layer behavior. Okay. Okay. And so from this, we can deduce, kind of a more kind of a detailed breakdown of what convection actually is. Okay. And so what we understand as convection is actually the combination of these two physical processes happening at the exact same time. Okay. Number one. And so the first process that that's going on, that's linked to the first point that we have above, is that convection is at least part conduction. Okay. Right, so remember we talked about conduction, the way conduction happens is that adjacent molecules are sharing energy with each other, right? And so some of that is happening here. And so, we have the fluid molecules, they're going to be in contact with the surface, and at a very, very micro level, those fluid particles are absorbing some energy from the solid or vice versa, okay? And so because we have this kind of molecule to molecule transfer of energy, at the very micro level, this is by definition conduction, okay? And so convection is at least part conduction. Okay? Okay. And the other part of convection has to do with the motion of the fluid, has to do with the fact that, as our fluid flows, then those molecules that we're using to transfer energy kind of flow along with the fluid, okay? And so convection is kind of the combination of these two things, and the combination of these two things produces, produces convection, okay? Right? And so this kind of tells us something that we kind of already understand by intuition, okay? So usually, convection heat transfer will be more enhanced compared to just pure conduction. Okay. All right. Any questions on this? Okay. All right. Another important takeaway that I want you to get from this, that's going to be important going forward, is that convection is very much a local phenomenon. And so what do I mean by local? And so what I mean by local is that, it's going to change, the amount of convection heat transfer is going to change from one point on the surface to another. Okay? Okay. And so if you had let's say we had an arbitrary potato, okay, and we were to flow fluid at it, okay. So let's say this fluid has some free stream temperature and some free stream velocity, okay. The amount of convection heat transfer that occurs at this point is going to be different than the one at that point, okay. And so that's something that we haven't really talked about yet. So what we've been kind of assuming this whole time using convection is that the convection heat transfer is the same across all parts of the solid, okay. But in reality, this just isn't true, okay. And so if I were to label this point 1, and let's call this point 2, okay. The reason we have different convection heat transfers at these 2 points is because the boundary layer is going to look different at those 2 points. Okay? right? So boundary layers are a very dynamic thing. And so the behavior, and so the behavior of the boundary layer, whether it be the thickness, whether it be the gradients, whether it be the nature of the flow, you know, at one point of the boundary layer is going to be very different than if you measure the boundary layer at a different point. So since the boundary layers is such a dynamic quantity, then it's going to produce different heat transfers throughout. Okay. And so that means, right? What that means is that you're going to have different values of H at these locations as well. Okay. Okay. Right. And so if you were to compute H or measure H at 0.1, you're going to get a different value of H at 0.2. Okay. Right. And so that's a problem. And so that's not something that we want to see, right? And so what we want, you know, ultimately what we want kind of, you know, and this is true in life, right? We want things to be as simple as possible, right? And so we want to use, you know, if we have a convection type situation, we want to have just a single H to kind of capture the whole thing, and we can use that H to perform thermal analysis for the entire object. Okay, but that's really hard to do when we know that, you know, the H is going to differ at different locations on the surface. Okay, and so for situations like this, you know, what we'll see is that instead of using a local H, what we do instead is we take an average H across the entire object. And one way that you can do that is you can use the average, I think it's called the average value formula from calculus. Okay, and so what you can do is that you can have H with a bar, where H with a bar here is the average H. Okay, this is equal to 1 divided by the surface area of the object multiplied by the integral of H. Okay, where this is a local H. DAS. Okay. And so that's something that we're going to be using as well. And so once we start going into specific kind of flow situations, I guess not next week, because next week we have the midterm. The week after that, you know, you'll see, you know, we'll use this formula to get a single H, which we can use to plug into like a thermal circuit like we've been doing. All right, any questions on this? Yeah. It just means average, yeah. Okay. All right, and so you know, I think that provides a good introduction for convection. Okay. Let me give you kind of a you know, a little bit more preview of where we're going. Okay. And so, you know, the way this unit is going to work is that we're going to spend weeks going over different kinds of flow situations, right? And so the week after next, we're going to look at what's called external flows, which are flows over kind of external objects, so things like airplanes, you know, things that are out in the open. After that, we'll go over internal flows, and so those are flows that occur kind of in an enclosed space, things like pipe flow, right? And then after that, I think we'll be going over something called free convection. Okay, but you know, no matter what unit that we're in, we're going to be doing the same process. The only thing that's going to be different is the details of the process that we're going to go over. And so let's talk about what I like to call the problem of convection heat transfer, or what I like to call convection heat transfer problems. Okay. Right. And so when I say that, we have a problem in convection heat transfer, or, you need to solve something, your goal is going to be to compute H. Okay. 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 But we've talked about, we talked about how difficult this is, because if because it depends so strongly on the fluid mechanics, and more specifically, it depends so strongly on the boundary layers, this is not going to be easy. And so what you'll see is that we're going to depend on another old friend for fluid mechanics, which are non-dimensional numbers. Okay. Okay. And so some non-dimensional numbers that we're going to use are things like the Nusselt number. Don't worry, you've probably never seen this before. If you have, then you probably shouldn't be in this class, but we're also going to use the Prandtl number. Okay. And what's nice about these non-dimensional numbers is that a lot of experiments have been done kind of over many years regarding their behavior. Okay. And so we're going to do two things. And so, we're going to depend on these non-dimensional numbers as well as their experimental correlations. Okay. Okay. All right. And so basically what you'll see is that, for certain types of fluid mechanics situations, whether it be external flow, turbulent flow versus laminar flow, internal flow, turbulent versus laminar, we have these experimental correlations of these non-dimensional numbers, which we can use to compute H. Okay. And then once we compute H, then we can perform analysis kind of exactly as we've used to. All right. Any questions on this? Okay, so actually that's a little bit beyond kind of what I had planned for today. So actually, let me, since the next class is the midterm, let me go ahead and call it here. And so, let's go ahead and pick this up after the midterm. Okay. All right. So remember, next class is going to be our midterm exam. So make sure you're here in person for that. Remember, you can have one sheet of notes, 8.5 by 11 sheet, both sides. Write it, type it, whatever you want, as long as you can read it. Bring a calculator, bring a pencil, and bring your brain. Yep. Yeah, yeah, definitely I would redo the homeworks, because the homeworks are going to come from the same, or the exam problems are going to come from the same brain as the homework, which is my brain. And so they're going to be written in very much the same style. And so, but if you're going to redo the homework problems, I would recommend you do them, try doing them without the solutions first, and then, and then look at the solutions after. Because I think what people tend to do is that when they say they're going to review homework problems, they just read the solutions. But that's not usually that useful for people. Then they kind of get into the trap of like, yeah, I knew that. Yeah, that's fine. But then on the exam, you're not going to have that. So yeah, I would definitely practice that. All right, question. So are you allowed to write examples on your notes? Yeah, sure. If you can fit it onto your sheet of notes, you can do that as well. You know, whatever you can fit onto the sheet of notes. You know, the only thing I don't allow on the sheet of notes is the answers to the exam, but hopefully that'll be impossible because even I don't know them until after the exam's done. So, so unless you can read the future, then you can't have that on your sheet of notes. All right, any final questions before we wrap it up for today? All right, thank you guys. So remember, exams on Monday, so I'll see everyone in class on Monday. Have a good weekend studying. Keep an eye out for the review video. It's going to be posted on Friday. I'll send an email out announcing that, and I'll see you then.
For him,
Yeah.
I'm literally sitting here like the whole day. Yeah, I'm gonna get some rockstar right now.
So for a lot of problem 4,
Yeah.
I'm using the formula for characteristic. And so for a cylinder, you know, you can, I mean, for most cases, you can probably just plug in the radius of the diameter. That's probably fine. But then what I did for all of these was just to kind of illustrate to you how to use it. I took the ratio of the surface area, and that's going to give you the characteristic. That's the length. I think it's going to be like the radius divided by. Yeah. So try doing the characteristic length, and you should be good to go.
I had everything set up. This is like a scaling issue. It was like -0.05.
Yeah.
And now it's like 15,000.
So this should be 1. I think you took 1, you divided by 1,000. You take 1, multiply by 1,000. That was 1 kilojoule per kilogram. Something.
You want in terms of joules?
You want in terms of joules, but that was 1 kilojoule. So 1 kilojoule is 1,000.
Oh, got it.
Yeah.
Thank you.
Yeah.
Professor, so
Yep.
on the notes, was this flow? So I couldn't really see what that said.
Yeah, it should be flow. So basically that just illustrates how, so that just illustrates how, you know, when you have a moving fluid, it's gonna move particles along.
Yeah.
So you have bulk motions.
Okay, and then, and the test this week, because I have this thing, do you
Yes.
prefer if I schedule with them or do I do with you?
You should schedule with them because I don't know, I think there's another class in here after this.
Yeah.
And so I can't have the room for longer than
Yeah, okay, I'll just make sure.
Yeah. So then, go ahead, schedule with them and and they'll send me an email.
Yeah, I
I'll
think
give
usually
them.
they send you email.
Yeah.
Send them.
I send the PDF.
Yeah, I think they after they put in your mail.
Yes.
Yeah, I think they usually put it back in the book.
Yeah. It's been a while, but I remember.
Yeah.
I remember.
Okay, thanks.
Yep. Mhm.